Hello students, today we are going to see limit points and isolated points. Limit points and isolated points. Isolated points. First we will see definition of limit point. Definition of limit point. Let order pair xt be a metric space. Be a metric space and A is a subset of X. A point X belongs to capital X is called a limit point or accumulation point or cluster point of A if each open sphere centered on X contains at least one point of A other than X. In other words, if SR of X means open sphere centered at X with radius R minus singleton X with intersection A is not equal to phi. The set of all limit points of A denoted by A dash is called the derived set of A. See here, what is the definition of limit point? X be a metric space and A is a subset of X. A point X belongs to capital X is called a limit point or accumulation point or cluster point of A if each open sphere centered on A contains at least one point of A other than X. That is, open sphere centered on X with radius R minus singleton X with intersection A is not equal to phi. The set of all limit points of A is denoted by A dash and it is called derived set of A. Let us see some examples on limit points. Examples. First example is, let RU be the usual metric space and A is a subset of R. First is, if A is equal to closed interval AB, if A is equal to open interval AB, if A is equal to semi-open closed interval AB, and A is equals to semi-closed open interval AB, then limit points of A is equals to closed interval AB. See here, what is the definition of limit point? X belongs to capital X is said to be limit point of A if every open sphere centered on X contains at least one point of A other than X. See here, why? If A is equals to, suppose A is equals to closed interval AB, then limit point of A is closed interval AB. Why this is? Because for all X belongs to closed interval AB, for all X belongs to closed interval AB, each open sphere centered on X contains at least one point of A other than X. Therefore, limit point of A is equal to closed interval AB. See here, suppose this is our closed interval AB. If you take any point X which is belongs to or does not belong to, which is belongs to closed interval AB, then see here, each open sphere, that is, if you take this open sphere or this, each open sphere centered on X contains at least one point of A other than X. Therefore, limit point of closed interval AB is nothing but closed interval AB. Now, what happens if A is equals to open interval AB? Then what happens? Then limit point of A is equals to closed interval AB. Why this is? See here, suppose this is a open interval AB. That is, A and B are not included in this interval. But if you draw any open sphere centered on A, that sphere contains at least one point of A other than this point A. Similarly, each open sphere centered on B contains at least one point of A other than B. Therefore, limit point of open interval A is nothing but closed interval AB. Similarly, limit point of semi-open closed interval AB and semi-open closed interval AB is closed interval AB. Let us take second example. If A is equals to 1, 1 by 2, 1 by 3 and so on, then limit point of A is equals to singleton 0. See solution of this problem. See here, what is A? A is 1, 1 by 2, 1 by 3 and so on. That is, this set is nothing but 1 by n. See here, what is this set? A is equals to 1, 1 by 2, 1 by 3 and so on up to 1 by n. As n tends to infinity, 1 by n tends to 0. Not exactly 0, means 0 is not included in this set. 0 is not included in this set. Therefore, for 0 belongs to R, each open sphere centered on 0 contains at least one point of A other than 0. Therefore, limit point of A is equal to 0. Therefore, limit point of A is equal to singleton 0. See here, this set is 1 by 2. Sorry. Suppose this is the interval 1 and 0. Here is 1 by 2, 1 by 3 and so on. If you draw each open sphere centered on 0 contains at least one point of A other than 0. Therefore, 0 is the limit point of A. But this is not true for remaining points. See here, if we take 1, what happens if I draw this open sphere? This open sphere does not contain any point of A other than 1. Similarly happens with 1 by 2 and so on. Therefore, 0 is the only limit point of A. Let us take third example. If A is equals to Z, then limit point of A is equals to 5. See here, we have A is equals to, here A is equals to Z. Z means only 0, 1, 2, 3, -1, -2 and so on. Okay. See here, if you take any point, suppose you take here 0, what happens? Each open sphere centered on X does not contain any point of Z other than 0. Therefore, 0 is not limit point for this Z. Similarly, 1 is not limit point for Z and so on. Therefore, for all X belongs to Z, each open sphere does not contain at least one point of, sorry, here only open, one point of A other than X. Therefore, limit point of A is equal to 5. That is, limit point of Z is equal to 5. Let us take fourth example. If A is equal to Q, then limit point of A is equal to R. Here A is equal to Q. Why limit point of Q? Q is nothing but set of all rational numbers. Its limit point is set of real number. Why this is? Because for all X belongs to R, each open sphere centered on X contains at least one point of A other than X. Therefore, limit point of A is equal to R. Therefore, limit point of A is equal to R. Fifth example is, if A is the set of all irrational numbers irrational numbers, then limit point of A is equals to R. Why this is? Because for all x belongs to A, each open sphere, sorry, here is R. Each open sphere centered on X contains at least one point of A other than X. Therefore, limit point of A is equals to R. Next example is, see, if A is equals to R, then limit point of A is equals to R. For all x belongs to R, each open sphere centered on X contains at least one point of A other than X. Therefore, limit point of A is equal to R. See here, this is a real line, 0, 1, -1 and so on. See here, if you choose 0, each open sphere centered on 0 contains at least one point of A other than 0. This is true for all real numbers. Therefore, limit point of A is equals to R. Therefore, limit point of A is equals to R. Let us see one theorem. Let XD be metric space. Let XD be a metric space and A is a subset of X, then A is closed if and only if A contains all its limit points. Proof. See here, what is theorem? XDB metric space, A is a subset of X. Then A is closed if and only if A contains all its limit points. We have to prove that A is closed if and only if A contains all its limit points. Okay. First we assume that A is closed. First we assume that A is closed. We have to show that A contains all its limit points. Here we can say that is A dash is a subset of A. A dash is a subset of, therefore, or here A contains all its limit points, that is A dash is a subset of A. That is we have to show that, here we can say that is we have to show that A dash is a subset of A. Okay. Let X is belongs to A dash. X is belongs to A dash means X is limit point. X is limit point of A. X is limit point of A, and hence every open sphere centered on X contains at least one point of A other than X by definition of limit point. Suppose X does not belong to A. Students, remember that limit point may or may not be belong to A. See here what we have taken. Suppose X does not belong to A. That implies obviously X is belongs to A complement. That is X minus A. But what we have assumed? A is closed. That means X minus A means A complement is open. Therefore, there exists R greater than 0 such that open sphere centered at X with radius R is a subset of X minus A, since X minus A is open. This shows that open sphere centered on X does not contain any point of A other than X, which is a contradiction to limit point, X is limit point of A. Therefore our assumption X does not belong to A is wrong. Therefore X is belongs to A. That implies A dash is a subset of A. That is, A contains all its limit points. See here, what we assume? A is closed. We have to show that A contains all its limit points. That is, we have to show that A dash is a subset of A. Let X is belongs to A dash. That implies X is a limit point of A, and hence every open sphere centered on X contains at least one point of A other than X. Suppose X does not belong to A, means X is belongs to X minus A, that is A complement. But A is closed, therefore complement of A is open. By definition of open set, there exists R greater than 0 such that SR of X is a subset of X minus A. This shows that open sphere centered on X does not contain any point of A other than X, which is a contradiction to X is limit point of A. Therefore our assumption X does not belong to A is wrong. Therefore X is belongs to A implies A dash is a subset of A. Let us prove converse part. Conversely, assume that assume that A dash is a subset of A, that is A contains all its limit points. We have to show that A is closed. We have to show that A is closed. That is to show that x minus A is open. That is complement of A is open. Okay. For this, let x belongs to x minus A. That implies x does not belong to A. Also, x does not belong to A dash. Why this is? Because A dash is a subset of A. If x does not belong to A, obviously x does not belong to A dash. Therefore, we can find an r greater than 0 such that SR of x is a subset of x minus A. That implies x minus A is open. That implies A is closed. Here, proof is very simple. Conversely, assume that A dash is a subset of A. Okay, we have to show that A is closed. That is to show that x minus A is open. Let x belongs to x minus A. That implies x does not belong to A. Also, x does not belong to A dash, since A dash is a subset of A. X does not belong to A. Therefore, we can find an r greater than 0 such that open sphere centered at x with radius r is a subset of x minus A. Means x, by definition of open set, x minus A is open. That implies A is closed. Hence, proof of this theorem is complete. Let us see definition of isolated point. Isolated point. If x belongs to capital X, for this let XD be a metric space. Let XD be a metric space and A is a subset of X and A is subset of X. If x belongs to capital X, is not a limit point of A, then there exists an open sphere centered on X which does not contain any point of A, other than X itself. That is, SR of A intersection A is equal to singleton A for some r greater than 0. Such a point x belongs to capital X is called isolated point of X. Is called isolated point of A. See here, what is definition of isolated point? X is not limit point of A, then there exists an open sphere centered on X which does not contain any point of A other than X itself, that is, open sphere centered at X intersection A is equals to only singleton X. For some r greater than 0, such a point X belongs to capital X is called a isolated point of A. Let us take one note. Every point of a metric space is either a limit point or isolated point. Limit point or isolated point. Limit point or isolated point. Let us take one example. Consider the metric space. Consider the metric space X is equals to set of all 0, 1 by n. N is belongs to set of all natural numbers with the usual metric given by the absolute value. Note that 0 is the only limit point of X, while all other points are isolated points of X. See here, in previous example we have proved that y0 is the only limit point for this set, and 1 by 2, 1 by 3, 1 by 4 and so on are the isolated point, because if you take 1 by 2 and draw a sphere around it, that sphere does not contain any other point of X other than 1 by 2. Therefore 1 by 2 is the isolated point for X. Similarly 1 by 3, 1 by 4 and so on. Therefore all other points are the isolated points of X. Okay, we will stop here. In next video we will see closure of a set.